Hey guys, welcome back once again. This is Nagaraj SK, lecturer of Computer Science and Engineering Department. So, in this video, we'll move to the lecture number 30 of Unit 3 Brute Force and Exhaustive Search. So, in this video, I'm going to cover depth first search of exhaustive search. So, what is depth first search, right? What is we have the exhaustive searches like uh, we can apply for depth first search and as well as breadth first search algorithms. So here the term exhaustive search can also be applied to two very important algorithms, that is that systematically process all vertices and edges of a graph. These two traversals algorithms are, that is depth first search, and one more is breadth first search. We will be learning that in the next lecture, so I'm going to cover only depth first search algorithm here. So these two algorithms have proved to be very useful for many applications involving graphs in artificial intelligence and operations research. And in addition, they are indispensable for efficient investigation of fundamental properties of graphs such as connectivity and cycle presence. So, we'll learn what is depth first search, right? So, once again, I'm going to brief you about what is exhaustive search, a brute force approach to combinatorial problems which require generation of permutations or subsets. Generate every element of problem domain and select feasible ones, the ones that satisfy constraints. And finally, find the desired one, the one that optimizes some objective function. Then, for both traveling salesman and knapsack problem, exhaustive search gives exponential time complexity. These are NP hard problems, no known polynomial time algorithm, and most famous unsolved problem in computer science, that is P versus NP problem. Look at you can go through that Wikipedia of what NP problem is and what P problem is. So we'll see in more detail in limitation chapter, that is we will be learning this in the limitation chapter. So here, the graph traversals of this depth first search algorithm, that problem domain can be a graph. Exhaustive search needs to visit each vertex and do something at it. And two important graph traversal algorithms, that is, as I said, depth first search and breadth first search. So, what is depth first search, right? Depth first search starts a graph's traversal at an arbitrary vertex by marking it as visited. On each iteration the algorithm proceeds to an unvisited vertex that is adjacent to the one it is currently in. And if there are several such vertices, a tie can be resolved arbitrarily. As a practical matter, which of the adjacent unvisited candidates is chosen is dictated by the data structure representing the graph. So, at dead end backs up one edge to the it vertex it came from and tries to visit unvisited vertices from there, then eventually halts after backing up to the starting vertex. By then, one connected component has been traversed. So, if unvisited vertices remain, DFS starts at one of them. Then here we have an example. Before going to this example, I would like to mention some more points about this depth first search. That is, it is convenient to use a stack to trace the operation of depth first search. So we push a vertex onto the stack when the vertex is reached for the first time. That is, the visit of the vertex starts and we pop a vertex off the stack when it becomes a dead end, that is the visit of the vertex ends. It is also very useful to accompany a depth first search traversal by constructing the so-called depth first search forest. The starting vertex of the traversal serves as the root of the first tree in such a forest. Whenever a new unvisited vertex is reached for the first time, it is attached as a child to the vertex from which it is being reached. Such an edge is called a tree edge because the set of all such edges forms a forest. The algorithm may also encounter an edge leading to a previously visited vertex other than its immediate predecessor, that is, its parent in the tree. Such an edge is called a back edge because it connects a vertex to its ancestor other than the parent in the depth first search forest. So this is about depth first search. So we are having an example here, and so we'll go through that. This is a graph here we are having, that is undirected graph. There is no direction from which to which vertex is pointing to which, right? So here we have tree edge, back edge, and depth first search forest, because those are two graphs in this and they are not connected. That is, one outer tree is GHJI, right? GHIJ. This is one tree and another is ABCDEF. That is another tree. So it will become together, it is become a forest, that is depth first search forest it is. So which data structure to use for this, right? So we can use depth first search for that. How to decide if the graph is connected? Start a DFS traversal at an arbitrary vertex and check after the traversal halts whether all the vertices of the graph will have been visited. If no packages, then it will become acyclic. If there is no packages in the tree, then it will become acyclic. So how to decide if the graph is acyclic, right? So we can decide with the help of depth first search algorithm. So here we have a pseudocode of this depth first search algorithm. That is, we have a method as a dfs and it is taking g as an argument. So this implements a depth first search traversal of a given graph, and the input we are passing to this algorithm is a graph g. That is, it will be having vertices and edges v comma e. So what output we are going to expect is, that is, graph z with its vertices marked with consecutive integers in the order they are first encountered by the dfs traversal, and mark each vertex in phi with 0 as a mark of being unvisited. So initially count will be 0, then for each vertex phi in v we are doing some operations. If v is marked with 0, then we are going to call dfs method by taking the value v. So dfs v will be get called. Then count will become count equal to count plus 1, then mark v with count. Then for each vertex w in v adjacent to v, we are doing, if w is marked with 0, then again we are calling with the uh, dfs method. So the traversal time of this algorithm is in theta of v square, or in theta of v plus e, number of vertices, theta of number of vertices plus number of edges, that is adjacency matrix and adjacency list. Next, summarize what we discussed so far. We discussed the following things like depth first search, working principles of depth first search and examples. So if you are having any doubts in this, please do ask your queries. Thanks for watching. Thank you all.